Now that we've seen including the axial term for our virtual work on frames is negligible, for this problem we're just going to focus on our equation based on the flexure. So we're trying to find the horizontal displacement of the beam. So 1 times delta x is just going to be little m big M over EI. So we don't have to worry about finding the axial force in these members. So first step is going to be determinacy. We do have a hinge on this problem, so we're going to have to cut there, which means n is 2 pieces. The reaction, we have 2 pins, is 4, plus the 2 internal forces we released are compared to 3n. We have 6 equal to 6. We are stable and determinate, which means we can find reactions using equilibrium. Before I jump to that, though, I am going to draw my virtual structure. Again, same geometry, same boundary conditions. So 2 pins, a hinge, and we need our virtual load, which I am going to put at the top of the beam to calculate that horizontal displacement. Our next step is going to be find the reactions using equilibrium for both the real and the virtual. So the first thing I'm going to do is, for the real structure, sum of the moments about A, call this A and B, find the vertical. So if I take a moment about this point, I have 20 times 15 clockwise plus 1 times 25 times 12.5 clockwise plus by times 25 equals 0. That's going to give me by is positive 24.5 kips upward. And once I have that, I can find my AY, summing my forces in Y. I have AY plus by minus 25 kips for my distributed load, and AY is 0.5 kips, also upward. Now if I try to sum forces in X, I'm going to get stuck, so this is where I need to break my structure based on the hinge, so I'm going to look at this piece. So I have found that this is 24.5. I don't know BX. When I cut there, I release axial and shear at that hinge. We'll just call that location C. So I could now do equilibrium on this body. I can sum my moments about C, and I find BX is 0. And I can sum my forces in the X direction, find BC is 0. Sum my forces in the Y direction, and find NC is negative 24.5. That information, I can go back to the other piece of my structure. Just 1 kip per foot. I already know this is 0.5 kips. I don't know AX. And I know that this NC, so I drew this one upward, so I should draw this one downward and throw the negative on it, or I could draw it upward as positive 24.5, which means that when I sum my forces in the X direction, AX is just going to be 20 kips to the left. So I have found all my reactions. I could repeat this process doing this for my virtual structure, so I'm going to skip doing it out, but you're going to take the exact same steps. I will just provide the reactions. So for this one, 0.5 kips, 24.5 kips, 20 kips, BX was 0. We're going to see this one is 3/5 up, 3/5 down, and 1, and we're going to see that 0 again on our reaction at the base. So we found our reactions, and we are going to then define our x-coordinates. I have 3 members. They have loads either at the ends or across the entire span, so I only have to make 1 cut per member due to the angle change between the beams and columns. I'm going to cut here, 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 and whatever I do to my real structure I have to do to the virtual. So I could draw this free body diagram, or this one for cut 1. Hopefully we can all agree that this one is easier. And for the next one, next cut, I can either draw everything to the left or everything to the right for that cut. Both of them look about the same, so I'm just going to stick with the pink one, which means when I go to define my x's, I'm going to start my x1 at the bottom of this column for the green highlight, and I'm going to start my x2 on this side of the beam for that left cut. And my last one, so I can either draw everything below or I could draw everything above. Below definitely seems easiest, so I'm going to stick with that, and I will draw this free body diagram. So there's my 3 free body diagrams I'm going to draw, because I am going to find the internal moments for each of these. These are going to be fairly straightforward. If I look at this free body diagram, hopefully we recognize, if I draw my moment, that there is no horizontal force, so my little m of x3 is 0. Same thing for my big M of x3, which doesn't matter as long as one of them is 0. And then I have, for my x1 cut, drawing a moment like this, and I'm going to find little m of x1 is just my horizontal force times the coordinate, so 1 times x1, which means this one is 20x1. So the only free body diagram I really need to draw, because it's going to be a little tougher, is my cut in the beam. So that's going to look like this for the real. I'm going to see my distributed load, my 20 kips, my x2 measuring from here, seeing the full length of, so I won't see x1. And I need my reactions, 0.5 and 20 kips. And where I've cut, I have released my m of x2. Draw the same picture for my virtual. Going to see the unit load I applied. Going to see my reactions. And I'm going to see my coordinate x2, as well as the moment I released, little m of x2. So I can sum my moments about the cut. Alright, we've got a lot happening, so let's see, this is causing moment, this is causing moment, the 20 kips is not, the 1 kip per foot is. So we've got 0.5 kips negative clockwise times a moment arm of x2 minus the 20 kips times a moment arm of 15 feet plus 1 kip per foot acting over x2 at a moment arm of x2 over 2 plus the thing we're trying to find, big M of x2. So this is going to be 300 plus 0.5 x2 minus x2 squared over 2. Moment here, so some moments about the cut. Little m of x2 is what we're finding. The one at the top is not causing moment, but the one at the base and the 3/5 are, so minus 1 times 15 feet plus 3/5 times x2. So little m of x2 is 15 minus 3/5 x2. Technically we need to write 3 integrals because we have 3 cuts, 3 moments, but because m of x3, both little and big, are zeros, we don't need that integral. So we're just going to write the 2. So 1 times delta x is 12 cubed over EI. Integral, do the beam first, 0 to 25 feet. We've got little m is 15 minus 3/5 times x2 times our big M of 300 minus 0.5 x2 minus x2 squared over 2 dx2 plus 12 cubed over EI for the column 0 to 15 feet. And we need our little m and our big M, which we said were x1 and 20 x1 dx1. And that will give us a delta of 2.47 inches. And we guessed it was to the right. We got a positive number, so it is to the right.